Hello, everyone, and welcome to 6-2 VL Summer 2021 Final Exam Question 10 walkthrough. In this video, I'll be going through the first three parts of this question. But before I get into the parts of the question, I want to go over what this question was about and why there were some of these requirements at the beginning. So the question, you were just given a bunch of statements about graphs and MSTs, and you were asked to evaluate whether or not they were always true, sometimes true, or always false. And so I want to explain these requirements because maybe they felt a little arbitrary, but they actually all have good reason to be here. Simple is because, well, we don't want to have any self loops. That's a pretty simple explanation. Connected, that makes the question that means that there actually is some MST, right? Because if it's not connected, then you can't even connect the graph. So there's no MST, and so it's kind of just done, right? It's a silly question to ask. Undirected is because we didn't talk about MSTs for directed graphs. So we stuck to undirected. Has at least one cycle. This is an interesting one, but it comes down to if you have a connected graph and no cycles, then it's a tree, right? And there's only one way to connect a tree, which is to use all of its edges. So the MST question is not very interesting if you don't actually have any cycles, right? Because it'll just be a tree. Okay, and then finally, the weights of all the edges are distinct. A lot of statements are kind of trivialized or not true if you allow for edge weights to be the same, because you can imagine MSTs with all the edges having the same weight. I mean, you could just solve that with a BFS, right? You don't even need any of these fancy algorithms. So with all edge weights being distinct is a much more complex and interesting problem. Okay, without further ado, let's get into the actual problem. So 10a, the statement was, for this part, additionally assume that the original graph has at least one negative edge, and then we just run Kruskal's as normal. So this question basically reduces down to, does Kruskal's work with negative edge weights? And that's an interesting question to ask, because as we know, our good friend Dijkstra's does not work with negative edge weights. Okay, so for this, let's take a look at some of the pseudocode for Kruskal's. So we basically create a disjoint set of the vertices, and then we sort the edges by weight in increasing order. And then we just go through that sorted list of weights or edges. And then we say, okay, if the U and V aren't connected yet, we connect them and we add that edge, okay? So let's think about it. If we had negative edge weights, how would that impact it? Well, they would show up at the beginning of the list, of the sorted list, which is fine because preferentially, if we're trying to minimize our cost, we probably want to try to use the negative edge weights first because those are the biggest bang for our buck, so to say. And then, we just see, okay, with this if statement, if they're in the same set, does this actually help us construct a tree? Does this help us connect things together? If it doesn't, don't bother with it. But if it does, go ahead and use it, okay? And so by the exact same logic that, we used to justify this entire algorithm, we can conclude that we can say that this sort of strategy will work even with the negative edge weights, because the strategy is as long as this edge adds it will connect new pieces together that weren't connected before, that's a good edge to use, okay? And so you want to use the minimal cost one. So the minimal cost one in this case just happens to have a negative value, but it's not really a big deal. So yeah, so this is actually totally valid and it's fine. So this is always true. Okay, 10b. So for this part, we're going to assume that the graph actually has exactly one cycle, and then we run DFS from just some random vertex in here, and we're going to break ties by the edge weight, and then we just output what DFS says. So for this, I'm going to actually share a whiteboard. Okay, cool. So I'm going to draw the most basic graph we possibly can, okay? That meets these requirements and that can work. Okay, most basic graph that meets these requirements. Okay, there we go. This is working. Okay, so then I'll just call them 1, 2, and 3. Those are the edge weights. Sorry, those aren't names of anything. Okay, so 1, 2, 3. Okay, let's try this algorithm actually. Let's just go ahead and run DFS from that vertex. Okay. So we're going to run for this vertex, and we're going to pick the least weighty edge. So we're going to pick this 2 here, right? So we're going to pick the 2 here. We're going to go cross it, and then we end up at this vertex. For some reason, okay, there we go. And then we're going to go down. Okay, we're going to DFS, we're going to go look at all the edges. And again, okay, we already visited 2. So our only option is 1. So we're going to go down 1. We're going to take this. Okay, and then we're done because we visited all the vertices at this point. So we ended up getting a tree that looked like this. And I think we can all agree that that is indeed the minimum spanning tree. So this algorithm at least has some merit. It will at least sometimes work, okay? The question is, does it always work? And for this, it's probably helpful to start looking at some other examples. Let me erase this iris 1. Okay. What if we started here, like in between the like 2 like edges that we actually want to use in our minimum spanning tree? Okay, let's run the algorithm. So we're going to pick the edge that has less weight, right? So that's this one. So we go down this one and we end up here. And then DFS, we're going to look at these 2 edges. So 1 and 3, we already took 1, so there's no point going back there. So we're going to take this 3. And at that point, we have finished looking at all our vertices, so we're done. So the tree we get in this case looks something like this, 1 and 3. But that's not the minimum spanning tree because we needed this 2 here. This doesn't work, okay? And it doesn't work precisely because if you put us between the 2 edges that like we wanted to, like the 2 minimum edges that like, or the smaller of the 2 edges, right? Or I keep saying it wrong. Basically, the 2 edges that are smaller, okay? If you put us between those, we can only pick 1 because whatever like you put us next to, we're gonna go and pick like only 1 of them, and then we'll just pick the 3rd one that you didn't put us next to because of how DFS works. So this algorithm doesn't unfortunately work. It would have been really cool, but it doesn't work. So yeah, so the answer to this one is sometimes true. That's just how it is. Okay, last part. We're going to run Dijkstra's. So this statement is we run Dijkstra's from every vertex in the graph for one step. So that from each vertex, we have found 1 edge, and then we add all the edges to a set and we output that set. So again, I think it's very helpful to look at like actual examples, okay? So let's just go ahead and back to our friend, this 3 vertex thing that meets the requirements of the problem. I don't know, let's just go and pick this 1, 2, 3 thing again. Okay, we run Dijkstra's from every single vertex. So we run it from here. Okay, well, it's going to pick this 1. We run it from the 2. Okay, and the reason it picks the 1 is because Dijkstra's is going to preferentially like look at vertices that like have lesser distance. So it's going to go and pick this 1 edge because that's less distance. Let's go ahead and run from here. We're going to pick this 2. And now let's run from here. We're going to again pick the 2, and because sets can only really store 1 copy of things, we just keep the 1 and 2. So that actually totally worked, right? And like it didn't matter the order in which we ran these things, right? So that works. So it seems like this at least will sometimes work, right? Which is really good. That's pretty cool. But let's see if it works in every scenario. Let's amp up the complexity. Let's try a 4 node thing. Okay. And I don't know. Let me just go ahead. I have maybe a rough idea as to when this won't work, right? Because one thing we noticed in the last example is that we picked the 2 edge thing twice. And we expect to pick an edge twice, right? Or we might pick an edge twice. But like, can we use that property maybe to break this algorithm? Let's go ahead and look at it. Right? What if I just did, this is 1, this is 2, this is, I don't know, e to the power of 23. And I don't know, this is e to the power of 24. You know, some big number. Okay, these are both big numbers. Okay, really big. Okay, I run Dijkstra's from here. I pick the 1. I run Dijkstra's from here. I'm going to pick the 1 again. I run Dijkstra's from here. I'm going to pick this 2, and I run Dijkstra's from here. I pick the 2 again. Okay, so in other words, the tree we get is like this. So as we can see, this isn't even connected. Okay. The actual minimum spanning tree would have been this, which is horrible, this e to the 23 thing, but like we don't even pick that edge, okay? We don't even pick an edge to finish the job, okay? So this is actually really bad. This algorithm doesn't even produce a connected tree. So we can't even, this just doesn't work, unfortunately. It was a cool idea, but it does not work. So the answer is it's sometimes true. As we saw, it can totally be true, but there are scenarios in which it won't be, so it's sometimes true. So so that's the first 3 parts of the question, and I hope to see you for the later parts of it. Ciao, ciao.